My talk is entitled on some exact solutions of certain nonlinear PDEs in partial differential equations in physics. And I would like to thank very much to the organizers of hypercomplex systems for invitation of me to participate in this seminar, and of course to be a chairman today. Thank you. And my talk is divided. It consists only two parts. The first part is devoted to Bogomolny equations of baby Skyrme model, more exactly speaking of a restricted baby Skyrme model. And the second part is devoted to obtaining some exact solutions of certain heavenly family equations. Well, Bogomolny equations, I think that a good idea would be to devote to this topic several sentences. Of course, Euler-Lagrange equations of many models in physics are nonlinear partial differential equations of second order. In his classical paper in 1976, Bogomolny derived the equations called as Bogomolny equations or Bogomolny equations. Sometimes the writings is different, and however, this very interesting that parallelly these equations were derived by Belavin, Polyakov, Schwarz, Tubkin several months before Bogomolny for SU2 Young-Mills theory, and similar results were obtained in Kosoya's paper, and only Professor Białyński-Birula cited this paper, Kosoya's papers, in this context, in context of Bogomolny equation. However, this name does not appear there. Okay. What about Bogomolny equations? Very classical approach, introduction. I think that is the most simplest example. Let's take into account scalar field theory. Model T24 with spontaneously broken symmetry. And of course, Euler-Lagrange equations for these models are as follows. We want to wonder how one can avoid solving of Euler-Lagrange equations. And it turns out that we can write the formula 1 as follows. Yes, and the last term last term turns out to be a total derivative of some polynomial of phi. So of course we can simply integrate it, and we can write down the formula 3 as follows. And Q we call, of course, as topological charge. And if we now require attaining reaching value, the minimal value by this energy functional, then this term must vanish. And vanishing of this term determines the left side of Bogomolny equations. And the very well-known solution of Bogomolny equation in this case is so-called kinic. So in this case, there is satisfied the following inequality, so-called Bogomolny bound, and this is very, very important fact that in this case, this inequality is saturated. However, this very nice feature is absent in many physical models. For example, in the case of classical full Skyrme model. In the case of classical full Skyrme model, not baby, Skyrme model, one cannot derive Bogomolny equation. And this is very interesting that Skyrme observed this fact before Bogomolny and before, of course, Belavin, Polyakov, Schwarz, Tubkin. Skyrme observed this fact in in the 60s. Or maybe it was 1961 or maybe 1960, but I don't remember what exactly, in which exactly his paper Skyrme observed this. Okay, so this is so-called classical approach to Bogomolny equation. Yes, we are looking at the formula for the energy function, and we are wondering how we can making a completion to square. The so-called completion to square, yes. And if this is possible, if the Bogomolny bound is saturated, then we can derive Bogomolny equation. Another approach to Bogomolny equations is the approach based on strong necessary conditions method. The strong necessary conditions method was proposed firstly by Professor Krzysztof Sokalski in 1979, and in 2001, Professor Bolesław Szafirski, he died almost exactly 5 years ago, pointed out that this was unknown how to implement boundary and initial conditions, as well as how to set the Cauchy problem in the case when we apply strong necessary conditions method. And during this talk, I will show the example of Bogomolny model, a way for satisfying Professor Szafirski's requirement, especially for replying to the question how to set the Cauchy problem. And this is first part of my talk. And in the second part of my talk, I will also show how to obtain so-called functionally invariant solutions of some heavenly family equations, asymmetric, but also some two other heavenly family equations. And baby Skyrme model, I will not talk about all the Skyrme model theory, and I would like to only briefly speak that what you know. Surely this very interesting model possesses solitonic solutions, very useful when we want to describe phenomena in words of baryons, and this gives a good description of low energy physics of strong interactions. And baby Skyrme model is an analogical model on plane, a toy model in comparison to the Skyrme model in three-dimensional space. And of course, in the case of baby Skyrme model, the target space is S2. Okay, in these both models, if we studying the case of static field configurations, in these both models, Skyrme and baby Skyrme, these configurations can be classified topologically by their winding numbers. Okay, and as this is well known, baby Skyrme model includes quadratic term, so-called term of nonlinear O3 sigma model, and quartic term. This is term very, very important, and this is term which is necessary to if we would like to avoid the consequences of Derived theorem, and the potential. The potential in the case of baby Skyrme model, if we want to obtain static field configurations with finite energy, the potential is obligatory. However, the form of this potential is not restricted. The Lagrangian of baby Skyrme model is as follows, and we restrict our considerations to the restricted baby Skyrme model, so we neglect this term, the sigma term, yes? And okay, we assume nothing about the form of a potential V. Of course, this potential must be differentiable function of the field variables. And we want to derive Bogomolny equations for ungauged restricted baby Skyrme model in 2 dimensions. We want to solve these equations exactly, to solve more exactly speaking, Cauchy problem. Yes, Cauchy problem. And maybe I neglect this text because the time is limited. Okay, maybe now a very short description of the concept of strong necessary conditions. This is very well known fact. Yes, we start from the extremum principle applied to the functional, for example, as follows, and we obtain the Euler-Lagrange equations. And now we can require that we can consider strong necessary conditions. So we require vanishing of these terms in Euler-Lagrange equations. This term, and this term. Of course, in many cases, the solutions of such equations, if they exist, are very often trivial. So a cure for such situation is as follows. We make gauge transformation of a functional term. We make gauge transformation, but here gauge transformation that have nothing common with the electromagnetic field. This is not gauging as if we consider a theory with electromagnetic. No, the gauge transformation has different meaning, and we gauge transformation in such way that this is such functional that its local variation with respect to u vanishes. So Euler-Lagrange equations are invariant with respect to this gauge transformation. However, the strong necessary conditions 12, 13, and 14, are non-invariant with respect to this gauge transformation. So we have a chance, an opportunity to find some non-trivial solutions. And if we apply the strong necessary conditions 12, 13, 14 to gauged functional, we obtain so-called dual equations. And how this works in the case of restricted by the Skyrme model? Okay, we make stereographic projection, and density of the energy functional has the form 17, and we make gauge transformation. The gauge transformation in this case, the essence of this transformation is such that we add to this functional, to the original functional, the density of the energy functional, we add 3 terms. The first term is the density of topological invariant, and the second term and the third term are, simply speaking, total derivatives of some functions which are to be determinated. So these functions, of course, must be differentiable functions. Okay, now such dual equations appear if we apply the concept of strong necessary conditions. The number of these equations is large, so we have to make these equations self-consistent. So we have the necessity of a reduction of a number of independent equations by an appropriate choice of the functions g1, g2, and g3. And as this is, I think that this everybody can think such ansatz exist only for some special forms of the potentials. So in the most cases of the potentials, for many nonlinear field models, such reduction is impossible. So in such case, we cannot obtain Bogomolny equation. However, as we see, this approach is successful in the case of restricted by the Skyrme model, and we make 2 operations. We integrate the equations 19 and 20 and 19 and 20 with respect to the variable omega and omega conjugated omega, and we obtain we get the equation 25, where the function f will be determined later. And now we make proper choice of a function g1, g2, and g3. We multiply properly the equations 21, 22, 23, 24 by the derivatives of the field variables omega and conjugated omega, adding by side optimization equations, and so far and so far. And we get this condition that the total derivatives of g2 with respect to x must be equal to the total derivative of g3 with respect to y. And we obtain such relations. Yes, and we obtain the conditions that the function g2 and g3 must be consistent. So the third term in the gauge transformation of the functional of energy vanish. The second and third term vanish. So only term which is present here is the first term. Yes. Okay. And what is later? Later we obtain such equation which is a candidate for Bogomolny equation for restricted by the Skyrme model, and we must only establish the form of a potential. Yes, and we insert these conditions and the equation 31 into the equation 25. Yes, and we apply Hamilton-Jacobi equation, and of course we obtain the such condition for the potential of restricted by the Skyrme model. So this potential must possess the following form if we would like to obtain Bogomolny equation for restricted by the Skyrme model. And I would like to add here that in 2017, in 2015, I obtained a stronger result. Namely, I had showed that there is no necessity to obtain Hamilton-Jacobi equation to obtain this condition for the potential. So, of course, the function g1 has to be as follows, and we have a Bogomolny decomposition, Bogomolny equation, because they are the synonyms for the given potential V. Yes. And okay, this was the Bogomolny equation, and now we would like to find an exact solution. And we insert here the potential of the form as follows: Mexican hat potential, namely very well-known model with spontaneously broken symmetry. And we use so-called hedgehog ansatz, and we formulate the Cauchy problem with the Bogomolny equation after inserting hedgehog ansatz here and formulated, and after formulating the boundary conditions for F, we have Cauchy problem, and we obtain some localized solution, but we of course in this case must require also such situations that the value of f of A and the energy must be constant in large distances. Yes, and we obtain such solution for the function f. It was the Lambert function, and for some concrete values of the parameters, we obtain the solution, and this is the solution, and this is this is the solution. And we can also show that the density of energy is localized. Okay, and now the second part, very quickly, some exact solutions of certain heavenly equations. asymmetric heavenly equations. There's very big family of so-called heavenly equation. This was started by Klebański in 1975 when he derived so-called first and second heavenly equation, and later many people were dealing with the problem of heavenly equation. The so-called asymmetric heavenly equation has been derived, general heavenly equation, and so far and so far. And now we would like to solve these equations analytically. Of course, many people also obtained many solutions, many exact solutions for these equations. And we apply here so-called structural decomposition method. This is not Bogomolny decomposition. This method was proposed by me in 2010. And very briefly speaking, in order to apply this method, we have to check whether it is possible to decompose the equation on the fragments characterized by a homogeneity of derivatives. For example, such case, yes, if there is a power of a derivative in the investigated equation, we have to find another derivative of a variable u, for example, the feed variable in this equation. But the power must be of the same order as the first. And if there is, for example, a second derivative, there must be also another second derivative, but in the power of order 1. And now we insert some ansatz in such equation. We obtain usually rather complicated equation. However, if we compute the all derivatives, we obtain such situation that there appear the total derivatives of the function f with respect to its first, second, or third, and so far arguments of this function. Yes, and now because
1 minute left.
Okay, thank you very much. So after applying this method, we obtain, for example, such situation, real general solution, real general heavenly equation, and real section of this equation, and the factors, the coefficients, A1, A2, and so far, must satisfy some algebraic relations. Thank you very much for your attention.